So, good afternoon, everyone, and thanks for making it this far into the conference. So, I'm Kassem. I'm going to be talking about the work we did last year about balancing the privacy and rewards requirements of both users and service providers in indoor location services. I did this work with Kyuhan Kim from HP Labs and Professor Kang Shin from University of Michigan. So, indoor location is the new frontier or the new trend in localization technologies. Lots of companies are jumping into this, and the objective there is to localize users in indoor environments within a few meters. Now, this is supposed to be a win-win scenario for both the users and service providers, such as retail shop owners. They monitor our mobility, they understand our preferences and behaviors, and in turn, they are supposed to provide us with improved services in the form of optimized product placement, improved checkout lanes, improved deals, promotions while we're shopping. So basically to make our shopping experience better. But unfortunately, these localization technologies, they have not been realized to their full potential, partly because of technical constraints, but majorly because of user privacy concerns. So to gain more insights about the shoppers' perceptions about indoor localization and tracking, we performed an online survey with 200 shoppers from two major US retailers, Nordstrom and Walmart. So we first asked them in a hypothetical scenario. We displayed a disclaimer, the same one that Nordstrom displayed to its shoppers in 2013. So we used the same language as a service provider to avoid any bias in our results. So we asked them, after seeing this disclaimer, do you consent to sharing your location or not? So consistent with previous surveys, around 61% of the participants or respondents are privacy-oriented, meaning that they reject tracking. 24% are neutral. They consent to tracking part of their mobility, while the rest are service-oriented or unconcerned, and they allow full tracking. So we went ahead and tried to analyze the dynamics behind each group's decisions. While there are more interesting results in the paper, we're going to be focused here on major three takeaways from the results. First, we asked the privacy-oriented participants to trace their latest shopping path when they shopped in either Walmart or Nordstrom. And then we asked them, do you consent to sharing the whole path that you traversed? Interestingly, 40% of these respondents indicated that they have no problem in sharing parts of this path, which means it's not really a clear-cut issue between reject and consent to tracking. There's some wiggle room there. Moreover, we asked the service-oriented participants if they would change their decisions if they were to know that the service provider is sharing their mobility with third-party entities, such as advertisements and analytics agencies. And now only 26% of these respondents still consented to full location tracking, with the rest answering we're not consenting, we're not sure. More importantly, 57% of the respondents indicated that they would utilize a technology that shares their mobility data, parts of their mobility data in a private manner in exchange of some rewards in return. And this gets us back actually into the keynote speech of yesterday. Most people are pragmatists regarding their data sharing preferences. But the problem is that the relationship, the privacy calculus with the more powerful service provider is biased against them. They cannot really estimate the long-term consequences of their actions, and they are tempted by the short-term rewards provided by service providers. So the question that we're trying to answer in this paper, can you provide a fair transaction between the user and the service provider? And to make a long story short, yes, we can, I think. So this is why we're proposing PRLBS, which is a framework that we designed, developed, and it tries to and aims to balance the privacy and rewards requirements of users in indoor location-based services. So before delving into the inner workings of PRLBS, just going to talk about the mobility model a little bit. So we abstract the layout of the indoor environment as a set of zones. Each zone is a semantic sub-area in the bigger area. You can look at it, for example, as an aisle in a supermarket. Transitions between different zones are modeled as edges. So basically we view the layout as a graph with zones and transitions or edges between them. And basically the user's mobility is a sequence of zones or a path on this graph. Now, the basic unit of exchange or interaction between the user and the service provider takes place when the user is transitioning from one zone to the other. And this is where the exchange between the user and service provider happens. So PRLBS, acting on behalf of the user, this performs an action whenever the user visits a new zone. This action could be hide the current zone, release the current zone to the service provider, or anonymize the current zone. Anonymizing meaning releasing a different zone. We can't really add a random noise or random location here, as the case of outdoor location privacy. In return, the service provider, or the opponent in this case, will respond with a service. We assume that the main communication channel between the service provider and the user is the shopper's app, such as Shopkick, for example. And we use the repeated play model of Tifarias and Megido of IBM Research in 2006 to abstract these interactions between the users and the service provider. And our objective here, PRLBS, acting on behalf of the user, is to choose the sequence of actions that maximizes the user's utility. And it performs that by consulting a set of non-human experts. So PRLBS has access to 3 experts. The first dictates hiding the visited zone all the time. The second dictates or uses a private location release mechanism that we're going to discuss next to decide on which action to perform, while the third expert dictates releasing the zone all the time. Now, to determine which expert to be chosen at runtime whenever we visit a new zone, a small exploitation trade-off happens here. With a very low probability, which is this very small text up there, a random expert is chosen so that we're guaranteed that we're sampling all the experts uniformly. And with a much higher probability, we choose the expert that has accumulated the highest utility thus far. After an expert is chosen, the expert, depending on the context, depending on the location, will tell us which action to perform, which is, again, hide, release, or anonymize. The performed action is going to entail a privacy cost to the user, and it's going to elicit a response from the service provider, which can be modeled as a received reward. Now, after the interaction finishes, we combine this reward and the privacy with the utility that we use to update the per expert utility, and then this interaction go on and on and on. So a few words on how we compute this privacy cost. So basically, we're dealing with an indoor environment, which is typically a public area. There's no notion of a private area per se. And it's really impractical to keep asking the user in such a small time scale, is this private, is this private, is this private? So we rely on a more objective metric, which is the information disclosure metric. So in a nutshell, and we're not going to go into details into this, we model the user's mobility as a probability distribution of the visited paths. Every time you traverse a new path, this probability distribution is going to shift a bit. The amount of shift is the new information that the adversary learned about us, and this is the information disclosure metric. To compute the received rewards, we leverage the interactions between the user and the service provider app. And basically, in particular, we measure the time the user spent interacting with the service provider's app as an indicator of the service received by the user. While that might not be the best way to compute the user satisfaction with the received service, it is a practical way. It's app agnostic, and we supported it by a few experiments and has been supported by vast marketing literature. So now we're going to talk a little bit about the second expert, which invokes a differential privacy mechanism to decide which action to perform. So recalling again, this is the layout. It's abstracted as a graph with zones abstracted at nodes and edges between them. Each edge has a weight of 1. The distance between 2 nodes is the number of edges on the shortest path between them. And the data release mechanism is pretty simple. So given the currently visited zone, release a zone at a distance I from the current zone with a probability P equals alpha to the power I Q naught. Now, provided some conditions, as stated in the paper, hold on alpha and Q, this mechanism can be proven to achieve epsilon dm differential privacy. With the probability of the observed path, given the actual path within an exponential bound of the observed path, given any other path P prime within a distance of the actually visited path. So to make it simpler, the adversary can't really tell which original path you traversed, and it's hidden within somehow a confusion set of other paths within a distance dm of the actually visited path. And we measure the distance with 2 paths as the added distance between them. So back to this layout on this flow diagram, how the PRLBS works. So we talked about the second expert. There's an action, there's a cost and rewards, and we need to estimate the utility. Now, utility basically is a function of the received reward and the privacy cost incurred. And it's really it's very user dependent. And every user has their own privacy rewards trade-off. So we can't really have a one-fits-all solution. So to address this issue, we allow each user for only one time to provide her own privacy rewards trade-off in the form of a table. So they can highlight their satisfaction level with each combination of privacy and rewards level. And as you can see, now we have like a set of rules. Like if the user enjoys full privacy, full service, then she's fully satisfied. So we use a Mamdani type fuzzy inference system to translate this table into a 2D function that maps the privacy and the rewards to the utility function. And then that can be used to update the per expert utility. So we implemented a device-based prototype for PRLBS. Basically, it's a standalone Android app. It's fully compatible with iBeacon localization. Apart from the workflow I described earlier, it has a BLE scanner, which keeps on scanning for BLE beacons as to build this layout that we described earlier. It has a collector module that measures app user interactions so as to estimate the service received. And it has an actuator module. So because we're dealing with BLE, the actuator was we instrumented Android to change the content of the BLE advertisements received by the app. But actually, you can plug in any location of Fuzcator here. Like in the case of Wi-Fi, you can take any of these published works before, plug them there. Because PRLBS basically acts as a control knob for these location actuators. And it features a UI where the users can put the privacy profile that we described earlier. We also evaluated the energy overhead of this app. Aside of BLE scanning, which the app is performing, which the service provider's app is performing anyways to provide the location-based service, it has very limited energy overhead. It doesn't have that much computation running in the background anyways. Finally, and very briefly, we performed a trace-based evaluation by leveraging 6 data sets from Crodad that has mobility, pattern mobility, and constraints environments similar to the one we're considering. And we also asked participants in our survey to trace their paths in Nordstrom and Walmart. So in the very first evaluation there, we asked also the participants at the Nordstrom and Walmart data sets to indicate their satisfaction levels, basically fill up a privacy profile. And then we tried to, after running PRLBS on their traces, we tried to interpolate their satisfaction values. Now, the main takeaway there, that most of the users are satisfied, which means that PRLBS is hitting their sweet spot in terms of privacy and rewards trade-off. Finally, we measured somehow the privacy guarantees offered by PRLBS by viewing how the portion of actually visited nodes that are released by PRLBS. For privacy-oriented users, and this result is consistent over all the databases, most of the users' visit zones are obviously not released. More interestingly, PRLBS does not release all the nodes or all the zones for the service-oriented users who may be unconcerned and might favor sharing. But the thing is, because of the information disclosure metric and because of the second expert, some of the mobility might be private, so not all of it is being released. Now, we also have more results in the paper showing that although we try to hide some of the users' mobility, the metrics used by service providers to analyze their patterns mobility in aggregate are somehow unharmed. So in conclusion, indoor location is important, it's gaining popularity. Users have privacy concerns. We have presented PRLBS that balances privacy and rewards in indoor environments, which hopefully we showed it's easy to deploy and usable. And the future work, planning to run a field study by deploying PRLBS in practice, probably doing more work on the UI and how to interact with the users to get their privacy decisions. And thank you.